Bismillahirrahmanirrahim. Sorry for the delays. Assalamu alaikum. This is Osama Ali, and I am the ex-student of the Glasgow Caledonian University, and basically belongs to Pakistan, Kashmir. So start with the presentation. The topic of the presentation is optimization electric vehicle battery charging and discharging in a microgrid environment. So basically, microgrid is a localized power system that can operate independently or is conjunction with the microgrid. So it consists of a distribution and energy generation sources like the solars, wind turbines, energy storage system, and the electric vehicles battery. In our right hand side, we can say the structure of the microgrid that basically a two-way communication with the electric cars, batteries, wind turbine, solar panels in the residential areas. And we can see here the base is a main grid that operate with the microgrid, and basically it's also by using the EPCC controller. It's also operate with the two-way communication. And the second diagram we can see here by using the voltage source converter. It's operate with the microgrid with the distribution energy generation sources. So electric vehicles are an attractive option for the integration of renewable energy into microgrid due to their ability to store and discharge electricity. So start with the electric vehicles introduction. EVs powered by the electric motor rather than the traditional combustion engine. So instead of the combustion engine, here we use the DC motors to operate the electric vehicles. So electric vehicles are powered by the rechargeable batteries, which are charged by the plugging the vehicle into electric outlets of the charging stations. We use these charging stations, or we can use the outlets like we can charge electric vehicles by using the oven-like system to charge it. So outlet can be our self-made or the home area services. So EV's battery can store the power off peak times and provide support to the grid at the peak time. In the UK, the off-peak time usually after 10 o'clock, 10 p.m. to 6 a.m. in the morning, and the daytime after 2 o'clock. So here the per unit the charges of the load became reduced, so we can charge on this time. Sorry. So this can help to improve the stability and the reliability of the microgrid, particularly the area which high levels of the renewable energy generation sources. So we know that all the generation sources that they produce the electricity, they can't use all the electricity on the same area. So we transmit this energy to another place, by using the transmission lines, or we transmit this energy to the main grid. So by using the microgrid, we can stable our system and we can make it reliable for generation areas. So my research question was how electric vehicles can efficiently integrated into microgrid while maintaining system stability and maximizing the use of the renewable energy generation sources. And the second one was intelligent charging and discharging scheme for the EVs with due respect to the upcoming tripping schedules. This is the complete simulation models of the EVs charging and the discharging system. First one is wind turbine that I used here. And second one was the solar panels that are the main source of the electric generation sources. And this is the battery management system that used for the battery charging and discharging. And this is the inverter that's used for the to operate the AC loads. And This one is battery, DC batteries. DC batteries basically, DC bus that is used to operate the DC load directly. And then these are the electric cars that used for the charging and the discharging. And these are some scopes that we get to. These are the scopes that we get the to take the requires measurement. So the system description. First, we describe this microgrids like solar grids, microgrid, solar panels, and the wind turbines. So the proposed microsystem consists of a solar panel, wind turbine, and the battery storage system. This is the block diagram of the solar panel. So we use the first solar panels and the maximum power point tracking and the DC-DC boost inverter. And in the wind system, we use the wind turbine, AC to DC converter, and the DC-DC boost inverter and the maximum power point tracking. I will explain further on the next slides. And here we use the battery storage system by using the DC-DC converter and the battery management system. And these are the building loads, and these by using the DC to AC inverter, because in the building we use the AC load, and in electric vehicle charging we use the DC, like DC supply, so we use the DC-DC inverter. So the battery storage system, which called the BCC, ensures balancing the microgrid between the produced energy and the loads required. So this is the solar system, and the that one is the simulation model of the solar system, and this one is the block model of the simulation system. So we use the solar panel, and we use the prototype and observe algorithm to get the maximum power point tracking of the system, and by using the converter like DC-DC, by boost DC-DC converter to get the required output. And here, and this is the block model, which consists of solar panels, DC-DC converter, and the maximum power point tracking, and the pulse width modulation, pulse width modulation generator. And this algorithm, like PO and O algorithm, that we used here to get the maximum power point tracking. And in the wind turbine, similar, we use this wind turbine, permanent magnet synchronous generator, and the AC to DC converter, and the DC-DC boost inverter. And the inner one is the simulation diagram. We use the wind turbine and the permanent magnet synchronous generator and the inverter. Basically, we use the bridge inverter, and then we use the maximum power point tracking as well, because we need to get the maximum power point tracking as well. So we use the prototype observe algorithm in similar way that we use in the solar panels. And some scopes we use to get our required output. And the complex work in my research was to make the battery storage system, like how the battery do the two-way communication to charge and discharge of the electric battery. Basically, it was a designer of the controller. So bidirectional DC converter is responsible for the balancing the power in the microgrids, and the goal was store excess energy from the renewable energy sources due to the low demand, and this stored energy then can be used to this supplement the power supply during the peak demand, or when renewable energy sources are unavailable. So we use the buck and boost mode for the battery charging and discharging system. Buck, like we charge, and this boost means we discharge the electric battery. So basically, you operate in two ways. So when the excess of energy, we have excess energy, then use for the charging, and we have when the available energy became reduced of a certain limit, then we discharge this electric batteries. So this is the complete simulation model of the battery controller and the bidirectional converter. And this is the battery controller. So basically, we use 400 volt for the DC vehicles charging. So these are the voltage, like available voltage. We compare this voltage. If the available voltage are became higher than the 400 volt, then the buck moves to operate, and the less than, then the boost move to operate. And this is the controller like this one, and this is the battery storage system. And with these are the oscilloscopes like this. That one is the main battery, fundamental battery that we use, a lithium-ion battery, and these are the scopes that we get for the required measurements. So this one is the microgrid battery management system. So here we see, by using the algorithm, if the state of charge is less than 20%, it goes down, and if the VDC voltage, like the available voltage, is greater than 400 volt, then battery stop charging. And if it's less than, then battery charging. And second one is, if state of charge between the 20% and 80% is yes, and then the battery start charging. Is if no, then battery start discharging. And the third word, the if state of charge is greater than 80%, then the battery became, and the VDC voltage is less than 400 volt, battery start discharging. And if it's less than is less than 400 volt, is stop charging. So I use the 5 electric vehicles for the charging discharging. So the batteries used in electric vehicles are the typically lithium-ion batteries, which offer high energy density and the efficiency and make them well suited for use in the electric vehicle. The electric motor in the car converter the electric energy stored in the battery into mechanical energy which drives the electric vehicles. So these are the inner structure of the electric vehicle. Basically, in like electronics, we just only 4 switches for the to make the electric vehicles. One for two we use for the charging, and the two use for the discharging. And this is the battery, like each electric vehicle's battery, that charge and discharge in a certain way. So we use the 4 types, like the algorithm, 3 types of algorithm. First one is charging, second one is charging, and third one is charging and discharging both. So first scenario was managing electric car charging the microgrid with sufficient power. So here we use the state of charge of electric, each like 5 electric cars, and we use threshold low and threshold high. Like what is the threshold low? Like how much amount that we use, like that we need to charge, and how much amount that is sufficient for the discharge. And main thing is the available power of the microgrid. If available power of the microgrid, we have like, if we set 50%, then the electric vehicle start charging, and if it's less than 20%, then it start discharging. Initially, the algorithm set the charging and discharging variable of each electric car to 0, and the microgrid power is evaluated to determine the appropriate charging and discharging strategy. If there is insufficient power to charge any of electric cars, algorithm turns without taking any action, because we don't have any electric power to charge electric cars. So if there is more than enough power to charge all electric cars, then the algorithm set the charging availability of all electric cars to 1. Because we have enough power to charge the 5 electric cars, so the 5 electric cars became start charging. And if the microgrid is not sufficient power, all the electric cars, because for the all electric cars, then the algorithm will evaluate the start of the charging of each electric cars. So algorithm see the state of each electric car, and any electric car with the state of charge below the low threshold is eligible for the charging. Okay, and the last one, the algorithm sets the corresponding charging variable to 1, indicating that the electric car can be charged using the surplus power. Surplus, I mean available power that you use for the charging. power algorithm variable in the microgrid. And after the algorithm evaluates the state of the charge of the electric car and determine the appropriate charging, it turns the final state of the charging variable for the each electric car. And the second one is discharging algorithm. A similar way, first is consider the state of charge of the five electric cars and the available power of the microgrid. Initially, the algorithm sets the discharging a variable of each electric car to zero, and then microgrid power is evaluated, and if it is less than zero, indicate of power defect the algorithm, then evaluates the state of the charge of the electric car. The algorithm will define an electric car with a state of charging of the greater than 50%, that we set the 50% as eligible for the discharging of the provide power back to the microgrid, which means if any of electric car have this 50% of the charging, so he start discharging. So, but and second thing is it must be available for the discharging as well. So subsequently, the algorithm sets the corresponding discharging variable to 1, indicating that the electric car can supply power back to the microgrid, and the after identify the appropriate electric car of the discharging algorithm returns the final state of the discharging variable for each electric car. First is the algorithm say the state of charge of the five electric cars. If any of them have the 50% or less than 50% they start discharging. If the state of charge any of them is not 50%, then he start like is reset of the all of the variables. And this one is start charging and the discharging. In this algorithm, the algorithm considers the state of the charge of each electric car, like S1, state of charge 1 to state of charge 4, 5, and low and high threshold are the state of charge, threshold and high and low, and the microgrid power, available power. The the algorithm initializes each electric car's charging and discharging set to 0 because in this state we do charging and discharging both at a time. If the microgrid power up like the microgrid power, its mean available power is less than equal to 0, indicating a power defect are insufficient because we don't have available power. The algorithm evaluates the state of charge of each electric cars. So algorithms see the state of charge of each electric car. Any electric car with a state of charge of the greater than 50%, because available power is not, we don't have any available power, then we need to get the charge from the electric cars. So we see which electric cars have the power of the greater than 50% is eligible for the discharging to provide the power back to the microgrid. So the algorithm sets the corresponding discharging variable to 1, indicating that electric car can supply power back to the microgrid. So if the power of the microgrid power is greater than equal to 500 kilowatt, then to charge our electric cars, because our each electric car is 100 kilowatts, so 5 electric cars are 500 kilowatts. So if microgrid power is greater than 500 kilowatt to charge our electric cars simultaneously, so the algorithm sets the charging variable of all electric car to 1. This indicates that all electric cars can be charged simultaneously, utilize this plus power available in the microgrid. So if the microgrid power is insufficient to charge our electric car, so the microgrid power is not available, then the algorithm evaluates the state of charge of each electric car. And then any electric car with a state of charge is less than low threshold for the charging, the algorithm sets the corresponding charging to 1. And then in the next stage, any electric car with a state of charge of the greater than high threshold for the eligible for the discharging. And then algorithm sets the corresponding discharging variable to 1, indicating that the electric car can supply power back to the microgrid when it is a power defect. And this is the electric vehicle in the controller simulation model. These are the controller, and these are the 5 electric cars, and these are the fundamental like rating of the whole system. We use the DC bus for DC voltage 400 volt, and the power is 100 kilowatt. That DC load that we use 100 kilowatt. The AC bus is 400 volt, AC volt, and the power that we use, like mean the load on the AC bus is 200 kilowatt with the frequency, because in AC we use frequency as well. So 50 hertz frequency. We use 926 ampere hour battery, and battery volt was 170 volt. And the PV panels we use 800 kilowatt PV panels, and the wind turbine was, this is the rating of the whole PV powers, and the wind turbine was 50 kilowatt. Each electric car is 100 kilowatt. So 5 electric cars we use, which means 500 kilowatts. So these are the input of the solar and the wind. So these are the solar radiation simulation that goes to up to approximately 900 kilowatt. Sorry, 900 solar radiation watt per meter square. And these are the variation wind speed variation. So which are in meter per seconds. So the produced power here we see is approximately, the produced power from the solar panel is 700, approximately 700 to 7,500 kilowatt, and the produced wind power is approximately between is to 500 kilowatt. And these are the battery state of charge. We see here it goes down on to 0. In the middle of 0.1, and then it goes up to this 70%. Yeah, because we see here here from 0 to, in this one we don't have any solar radiation, so that's why it goes down. And then in this stage we get the solar radiation, it goes up, this goes up. And in similar way we don't have here the available power, because the wind turbines have only less amount than the solar power. That's why the effect of of the of the of the battery is lower than of the wind turbine. So these are the loads we see here. As we see, we use the 200 kilowatt of the 200 kilowatt AC load, and 100 kilowatt is DC load with 400 volt. So we can see here the waveform of the DC and AC bus, and this is the 50 hertz frequency that we use for the AC bus. And one of the most important thing, when we use electric cars for the charging discharging, they must be available. So for the availability of the electric cars, we use this signal. So this mode is important when some of the microgrid vehicles need to be charged, since they have a charge below 20%. So in this case, the microgrid must have enough electricity to enable the charging produce. It's important to remember that the cars can only be charged if they are accessible. So here I just mentioned 2 electric cars. Car 1 is available on 0.2, and the car 0.2 seconds, and the electric cars 2 is available on 0.4 seconds. So this one is microgrid available power. So here we can see from 0 to approximately 0.6 seconds, we have a huge amount of available power. Then it goes down. So by using this one is first scenario, charging scenario. Like we see 3 algorithm. So this one is charging scenario. From 0.0 to 0.2, the state of charge of electric car is 0 because the first car is available on 0.2. 0.2. Here we can see it starts charging up to 0.6 because we have until 0.6 we have this huge amount of power to charge the electric cars. When the available power state of charge reaches to next to the 0.6, next to the 0.6, the available power goes down, so it stop charging. The next electric cars is available on 0.4, is 0.4, start charging because we have the available power. And similar way, when it's reached to the next to the 0.6, stop charging. And in such scenario, we see for the charging it is important that the state of charge of electric cars should be less than 20%. So here we see the state of charge of third electric car is 50%. So we don't need to charge this one. In the third electric car as well, the state of charge is 75%, no need to charge. And the third electric car is 73%, no need to charge this one as well. In this discharging scenario, for the discharging scenario, it is important that the state of charge of electric cars should be sorry, should be the greater than 50% to discharge electric cars. So in the first electric cars, we see the state of charge is 30%, no need to discharge. 40% second car, no need to discharge. And these are the available power of the microgrid. In third electric car, third and fourth electric car, we see the state of charge is above 50%. So these electric cars should be discharged. So when you start discharging, when the microgrid available power is less than it goes down. So when the available power is 0.8, we see here in 0.8 here the available power of the microgrids became 0. Then the electric cars 4 and 3 they start discharging simultaneously. And in this electric this stage, the state of charge of the 5 we see here is 73%. It should be discharged because of the discharging of these two electric cars, we have enough power, so we don't need to discharge this electric car as well. And these are the discharging scenario and charging scenario together. So we see here the first electric car available on 0.2, and is the available power is we have enough available power. Start charging, and then it's reach similar way, and next to 0.6 stop charging because we don't have available power in this stage. And in this stage, like this second electric car is discharging scenario. So discharging, when you start discharging, when first one is first condition is above 50%, it is above 50%, it deserve to discharge. And when it's reached to the 0.7, next to 0.7, we don't have available power, so it must start discharging. And third electric car is this electric car is available on 0.4, so it start discharging. 0.4 is available, and the state of charge is 13%, is below 20%. Start discharging charging, and we have available power as well. Is start charging next to the 0.6%, and next to 0.6% is the available power becomes 0, and then it became constant. And this third stage, like 4 electric cars, is similar way operates. And the 5 electric car, we see in the fifth electric car, in the fifth electric car, it deserves discharging, but we have enough power. We don't need any power on this stage. And these are some references. Thank you very much for your cooperation in listening. So do you have any questions? So you can contact me by using my email address. So I mentioned the email address in my first slide. Thank you very much.